Hello. So yesterday we have seen scalar triple product of three vectors, which is given by the formula above. So now what we will do is we will do the vector triple product, which is given by the formula below. And also we will be doing product of four vectors. So let's just start with the vector triple product. There is nothing much to understand about this one. It is just a formula. For now, if there is some kind of explanation afterwards, I will do it. But for now, I don't see a need for me to explain what the vector triple product is and how they reach that conclusion. Okay, so remember that we are trying to create a product of three vectors. So we have successfully done it with the scalar triple product yesterday. We had three vectors A, B, and C. So also today we will be having three vectors A, B, and C, and we will form a vector out of those three vectors A, B, and C. So let A, B, and C be three vectors. The vector triple product of A, B, and C is given by is this vector A cross B cross C. Some of you may be wondering, okay, some of you may be thinking that we won't need to write this brackets over here, but in fact the brackets are compulsory. You must write them. It is not like when you were having the scalar triple product. Over here it is really necessary because this one is actually it's unequal to this A cross B cross C. This vector and this vector, they are not equal, so that is why it is necessary for you to write the brackets. This is because vector multiplication, it's the cross product is not associative. That is why we really need these brackets over here. For example, okay, when you are having 1, 2, 3 and 5, okay, if you multiply them, you don't even need the brackets, because if you multiply these numbers, it gives the same result, 2, 3 and 5. Okay, it gives the same result. That is why you don't even need to write these brackets when you are multiplying real numbers. But over here, when you are forming the cross product of three vectors, you really need the brackets. Okay, because cross product is not associative. That is the reason. So this one, the formula for this one, it's actually given by, okay, maybe I will state it as a theorem. Again, you can try to prove by yourself. The theorem says that A cross B cross C is equal to, okay, the formula below, A dot C B minus A dot B C. So this one is actually a theorem, and you need to memorize this one. Okay, the proof is simple. Okay, you can do it on your own. I will just give you the starting point. Let A equal A1i plus A2j plus A3k. Similarly, let B equal B1i plus B2j plus B3k, and let C equal C1i plus C2j plus C3k. After doing this one, what you will need to do is you can find the left hand side. Okay, calculate the left hand side. How much is it equal to? Okay, to calculate the left hand side, just see you have to calculate B cross C first, and then take the cross product again with A. After finding out the right hand side, you can again find the right hand side. Okay, and then after finding the right hand side independently, you will see that both of them, they are equal. Okay, so I leave the proof to you. Okay, make sure that you complete it. Okay, but what we will be doing now okay, is in fact the product of four vectors. I will do exercises based on triple products and product of four vectors later, but for now, let us just have a clear idea of what these products are. And also, I forgot to mention that you are having a formula for this. Okay, the formula which is given below, it's for this. But what if you want to calculate, but what if you want to calculate something like this? Okay, so if you want to calculate something like this, okay, of course you can do it in the usual way. You can form the cross product and then take the cross product again with C, but taking the cross product is too complicated. Okay, so if we have to use a formula for this one, you can actually bring this C to the front. Okay, because as you see this formula that we are having, this formula below, it works only when a single vector is in front. Okay, and the two vectors should be at the back, whereas over here the two vectors are in front and the single vector is at the back. So what we can do is we will bring this single vector to the front by writing it as minus C cross A cross B. We can do this because the cross product, if you interchange the order, okay, you will have a minus sign. So the minus stays as it is. Actually now we can use the formula, okay, because C, A and B, okay, the two vectors are behind and now the single vector is in front, so we can use a formula. Just have a look at this. Okay, this will come in handy later. So the formula for A cross B cross C, it is A dot C B minus A dot B C, which is the formula again below. So now we will use this one, but instead of A we are having C, instead of B we are having A, and instead of C we are having B. So we will be having the formula something like this: C dot B A. If you replace these vectors over here in this formula, we will be having this minus C dot A B. Okay, so this, if you want a formula for this one, you can do it like this, just by bringing the vector to the front. Actually, I also forgot to mention one thing. Why exactly do we need this formula? Why exactly do we need that formula below? As you can see over here, you are calculating the cross product twice. Okay, always remember this. To calculate the dot product, it is easier compared to calculation of the cross product. You have learned it because cross product involves the determinant. Okay, so it is slightly tedious. So that is why we are expressing the cross product in terms of the dot product. As you can see over here, the dot product can be easily calculated, and over here again the dot product can be easily calculated. You should know that there is no symbol, there is no dot over here, and there is no dot over here. Kindly keep a note of that. Okay, so that is all about vector triple products. If we ever need something, maybe when we are doing exercise, I will explain it then. But what we will do now is product of four vectors. So before we are having three vectors, so now let us have four vectors. Okay, let A, B, C, D be four vectors. Now let us form a scalar product. Okay, we want a scalar product of the four vectors. This is actually Lagrange's identity. Okay, he formed this scalar product. Okay, he found a formula for this, Lagrange's identity. This identity, it states that if A, B, and C are four vectors, okay, I will write it again. Then A cross B dot C cross D, it's equal to the determinant A dot C, A dot D, B dot C, B dot D. So it's equal to this determinant. Okay, you should note one thing, that this one, it is a vector. It is a vector because it is a cross product of two vectors. Similarly, this one is a vector. Vector times vector dot a vector, it gives you a scalar. So that is why it is called a scalar product. And you are involving four vectors, so that is why it is called a scalar product of four vectors. And you should note over here also the determinant. This one, it is a scalar because it is a dot product. Scalar because it is a dot product. Similarly, scalar, scalar. If you take the determinant of this one, it will be a scalar. Alright, so we will try to prove this. Okay, proof. Okay, this is the proof for Lagrange's identity. The proof goes like this. Okay, let us just take the left hand side. The left hand side, it's equal to A cross B dot C cross D. Okay, so what we can do over here is we can replace A cross B by another vector. Okay, why we are replacing it? So that it will turn into a triple product. Because A cross B, it is a vector, so we can replace it with maybe another vector. Okay. Or maybe we can even replace C cross D with another vector. Okay, it will still work out. Okay, so let's see. A cross B dot, instead of C cross D, what I will do, I will write it as Q. Okay, I will write it as Q, where Q equal C cross D. So now this one, it is actually a triple product, because if you remember, if we are having a triple product, A dot B cross C, we can easily write this one as A cross B dot C, because the dot product, the dot and the cross can be interchanged in a triple product. So if you notice this one, it is actually a triple product, a scalar triple product as given by the formula above. So this one, we can write it as A dot B cross Q. Okay, by interchanging the dot and the cross. So what this will do is, now you remember, we can calculate the cross, we have to calculate the cross product first. So I will write it inside a very large bracket. B, it is still B, but now we can replace Q again. Q, it is C cross D. So this is what we are having. Okay, so A, it stays as it is. Now we will calculate this one. If you notice this one, it is a vector triple product. We can use the formula below. Okay, so if you are using the formula, you will be having B dot D C minus B dot C D. So if you are using the formula for the vector triple product, you will be having this. So over here, the reason is by using the formula for vector triple product. Okay, so we are almost done. So what happens is, now we can use the distributive property of dot product. Over here you are having a minus sign and you are having this dot product. So we can use the distributive property. We can write A dot this one minus A dot this one. But one thing that you should note, that this one, it is a scalar. This one, it is a scalar. Nothing in between. Okay, there is no dot, there is no cross. Okay, it is just like writing maybe something like this, 5a or 5c. Okay, because this one, it is a scalar, so it's just like writing 5c or maybe writing something like this, mc. Okay, similarly this one, it's just like writing nd. So what happens with scalar is we can take it to the front. So if you are taking the dot product of this and this, you can actually write it as b dot d. Okay, the scalar, you can take it to the front, and then a dot c, a dot c. Again, nothing in between. Minus a dot d, okay, so I'll write it behind. And over here, b dot c, it is a scalar, we can take it to the front. So we will be having something like this. So if you notice this one, it is, okay, maybe I made a mistake. b dot dc minus b dot cd. Okay, so if you notice this one, we can actually write it as a dot c, a dot d, and b dot c, b dot d. Because if you expand this determinant, this one times minus this one, okay, which is this. So this proves Lagrange's identity, okay, which is the complete proof for Lagrange's identity. Now we come to the last topic for today, which is the vector product of four vectors. Okay, so as you can see, the scalar product of four vectors, we have a formula by using Lagrange's identity. Similarly, for this one, we have a formula, but it may be difficult for you to remember. Okay, but anyways, I will write it down. It is alright if you forget the formula. We can still do some exercises even if you forget the formula for this. But the formula for the Lagrange's identity, do not forget it. So again, over here, let A, B, C, and D be four vectors. So because we want to form a vector product, so this one will actually have four formulas. Okay, we will be having four formulas. Two formulas. Okay, you can use any one of them. I will not write it down right now, okay, but what I want you to see is that we can easily fill what these things are just by doing the derivation. Okay, I will do the proof. Okay, so right now you may be thinking, what should I prove? I will prove the formula, but then I will fill in the formula afterwards. Okay, so again, we will start with the left hand side. Okay, it's equal to A cross B cross C cross D. So again, we can put this one as P. Okay, P cross C cross D. Okay, where P equal A cross B. Okay, so we can do that. We can do this. Now again, if you notice this one, it is the vector triple product as given by the formula below. So you can write this one as P dot D C minus P dot C D. Okay, so this is what we will be having. So we can write it down as P, now replace it by A cross B dot D C minus A cross B dot C D. So this is what we will be having, and if you notice the thing that is inside the bracket, it is actually a scalar triple product. Again, remember that we can interchange the cross and the dot. So over here we can easily write this one as the box product ABD C minus the box product ABC D. So this is the first formula that we can write over here. Again, as you see, the formula, it doesn't take too many lines to fill in. So even if you forget it, you can derive it from the start. You just have to remember the technique that we are using. Okay, so this is the formula. Again, you should note one thing. Over here, there is no dot or no cross, and similarly over here, no dot or no cross. Similarly over here, because this one it is a scalar and this one it is a vector. If you are having a scalar and a vector, you cannot put a dot or you cannot put a cross in between. For example, you cannot write something like this. 5 cross A, you cannot write something like this. Okay, but you can just write down as 5A bar. This makes sense, this does not make sense, and this does not make sense. I hope that is clear. So this is the first formula. Okay, so the formula for this one, we are having two of them. Okay, which is equal to the right hand side. Okay, which proves 1. Okay, if you name this one as formula 1. So this is the proof of formula 1. Okay, you can proceed it like this. But also the left hand side, we can proceed in another way. Then we can also have a different formula. Let us see. So this is what we are having. Again, the left hand side, we are starting with the same thing. Remember that in the first case we were replacing this one with B. Now we will replace this one with Q. Let us see. Let us see what will we have. Okay, so this is again a product of 3 vectors, but we cannot use the formula below because the single vector is at the back. So we have to bring this one in front first. So we will be having something like this. I forgot to write where Q equal C cross D. So again, write Q to the front. We will be having something like this. So now the single vector is in front. Minus, okay. So now we can use the vector triple product formula for this one. You'll be having Q dot B A minus Q dot A B. So you can actually take out multiply both sides, multiply the minus inside. So you'll be having Q dot A, but Q is C cross D. C cross D dot A B minus C cross D dot A dot B A. So this is what we will be having. Again, you notice that this one, it is a scalar triple product. So you can write this one as a box. CDA B minus CDB. So this is the second formula. You can even arrange this one. If you remember yesterday, if we are having a box product, we can easily interchange this one. So this one you can easily write it down as ACD B minus BCD A. So this one is the second formula that we can use. ACD B minus BCD A. This one is formula number 2. So this one is equal to the right hand side, number 2. Okay, so this completes the proof for both the things that we want to prove, the Lagrange's identity, which is the scalar product of 4 vectors, and the vector product of 4 vectors. That is all for today. Next time we will be doing exercises based on all the things that we have done so far.